What if I told you, you can detect whether all characters in a substring appear the same number of times, using just one mathematical condition? No sorting, no comparing every frequency, just one line. And once you see it, you can't unsee it. Today we're solving 3, 7, 1, 3. Longest balanced substring, part 1. And this one hides a beautiful little math equation. Let's jump in. We're given a string S consisting of lowercase letters. We need to find the length of the longest substring, where all distinct characters appear the same number of times. Keywords: substring, contiguous, distinct characters, same frequency. Example 1. Input ABBAC. Output for Y. Because ABBA forms a valid substring. It has appears 2 times, B appears 2 times, balanced. Example 2. Input, quote, ZZABCCY, quote. Output for the balanced substring is ZABC. Each character appears exactly once. Important realization: balanced does not mean frequency must be greater than 1. Even frequency 1 is perfectly valid. Let's think. Suppose in some substring there are distinct characters, and each appears k times, then total length equals distinct times k. This gives us a powerful condition. A substring is balanced if length equals distinct times max frequency. Because if all frequencies are equal, then the max frequency must equal every frequency. That's the mathematical trick hiding in this problem. And that is the beauty of this question. Let's think like beginners first. How do we generate substrings? 2 loops, left pointer, L, right pointer, R. For every L, expand R. Maintain a frequency array, track distinct characters, and max frequency. Then check if length equals distinct times max frequency. Boom, balanced. Since the constraints are 1 less than or equal to n less than or equal to 1000, O of n squared is totally fine. And that's exactly what this solution does. Now let's translate the idea into code. We define n as the length of the string and initialize the answer to 1. We iterate over every possible left pointer, L. For each L, we reset a frequency array of size 26, the distinct counter, and the maximum frequency. Then we expand the right pointer, R. For every character, we compute its index, update its frequency, and if it appears for the first time, increase the distinct count. We continuously update the maximum frequency. The current substring length is R minus L plus 1. And here comes the key check. If length equals distinct times max frequency, then the substring is balanced. We update the answer. 2 nested loops. O of n squared. Clean. Mathematical. Elegant. Outer loop. For L in range n. We fix the starting index. Frequency array. Frequent equals 0 times 26. Since lowercase letters fix size 26. Super efficient. Track distinct characters. If frequency at IDX equals 0, increase distinct by 1. Only increase when character appears first time. Track maximum frequency. Max underscore frequency equals max of max underscore frequency and frequency at IDX. We don't need to compare all frequencies every time. That's the optimization trick. The magic condition. If length equals distinct times max underscore frequency. Why does this work? Suppose max underscore frequency equals k. Distinct equals d. Then length must equal d times k, meaning all characters appear exactly k times. If even one character appeared less, length would be smaller than d times k. If one appeared more, max underscore frequency would increase. So this condition guarantees uniform frequency. This is the aha moment of the problem. Complexity analysis. Outer loop. n. Inner loop, n. Frequency update, O of 1. Total time, O of n squared, space O of 1. And since n is less than or equal to 1000, this comfortably passes. Common mistakes to avoid. 1. Recomputing all frequencies each time. 2. Sorting the frequency array. 3. Forgetting to track distinct characters separately. 4. Checking if all frequencies are equal manually. Slow. The mathematical condition saves you from all that. Elegant, fast, powerful. Think of it like this. Imagine you're filling buckets. Each distinct character is a bucket. Balanced means all buckets must have the same water level. And instead of checking every bucket, we just check total water equals number of buckets times tallest bucket. Elegant. Can we optimize further? Since n is less than or equal to 1000, this solution is already optimal enough. But for larger constraints, we'd need prefix frequency compression or advanced hashing of frequency states. That becomes a much harder version. Whenever you see all characters appear same number of times, uniform frequency, or balanced substring, think length equals distinct times max frequency. That single equation unlocks the problem. If you're enjoying these pattern-based breakdowns, hit like so YouTube knows you love smart tricks. Subscribe if you want to master Leetcode without memorizing nonsense. And here's your challenge. What's the longest balanced substring in AAABBBCCCAAA? Drop your answer in the comments and tell me how you approached it. Comment your favorite technique below, and I'll check it. See you in the next one.